All right, guys, here we go, kicking off chapter 3, the wonderful world of exponents and logarithms. So quick terminology here as we look at a general setup of an exponential function. So you have your leading coefficient right here, that's the a value. B represents the base. The base is whatever your exponent is attached to, and then our variable is going to be in the exponent spot. So it makes these guys exponential functions. So a couple quick reminders on these, and I'll just go through these real quick for you. If we had the function of 3 to the x power, and we were plugging in all these values for x, couple reminders on the rules. So obviously if you plug in a positive, it's very straightforward. 3 to the third power would just be 27. Plug in a 0, anything to the 0 power is 1. So don't forget that one. Negative exponents cause you to flip your base. So we do a reciprocal. So if I have 3 to the negative second power, that's what's going on right here. It flips, becomes 1 over 3 to the positive second power. So anytime you flip your fraction, you are changing the sign of your exponent. And then we would simplify from there and call it 1/9. If you see a fraction exponent, remember in a fraction exponent, the top number is your exponent and the bottom number is the root. So this would be like saying, so if 3 is my base, so 1 is to the first power, and we're doing a 4th root. So 3 to the 1/4 power would be the 4th root of 3 to the first power. And then we'd either leave it like this, or we could always do in a calculator if it calls for it, and then if you get just a combination of stuff, so now we have the negative and the fraction exponent, you just got to remember it's just a combination of the rules that we've already talked about. The negative is going to cause your fraction to flip, so it becomes 1 over 3 to the 3/2 power. Remember that the top number is your power, so it's a third power, and the bottom number is your root. So it's going to be a square root. So I have square root of 3 to the third, and then we just simplify as much as we can, and we will be working with simplifying radicals. We'll get into that later. Just wanted to remind you of a couple of those basics. So here's just a few that you can try if you want to try some for practice. You can pause and give these guys a shot. I'm just going to go through it real quick. So this is now 4 to the x, so if I did 4 to the second power, obviously that would be 16. Anything to the 0 power is 1. If we did 4 to the negative third power, remember that just causes us to say 1 over 4 to the third. And then if you clean that up, you would just get 1 over 64. If we did a 1/2 power, remember the top number is your exponent, the bottom number is your root. So this is like saying the square root of 4 to the first power, which is just 2. If we did a negative 1/2 power, it's the exact same thing, except that it causes our base to flip. So instead of it just being 2, it would be 1 over 2 for the answer. And then if we did a negative 3/2 power, again, it causes our 4 to go on bottom so that the exponent can become positive. The bottom number is the root, so this is a square root, and the top number is your exponent. Whenever you're doing these, you do have the choice. You could either square root the 4 and then do the exponent, or you can do 4 to the third power and then square root that. So it's really whatever you see is easiest. Typically, I would say let's do the square root first. So square root of 4 is 2, and then 2 to the third power would be 8. So we get 1 over 8 if we simplify that. On the next page, one of the things that we're looking at here, and you can always go through the example that you see up above if you need another example, but I'll kind of, well, let me just tell you, we'll do it this way. I'll show you their example, and then you can try one on your own, like we were doing on the other. So think of your general layout of an exponential function, right? They're calling a the leading coefficient, b is the base, x is the exponent. So what they're saying is what if you had a table of values? How would you figure out what the function is? How would you figure out what number is a and what number is b? A will be super easy to figure out because all you have to do is figure out what is the result when my x value is 0. So if we had, so this is the table where it came from on the previous page. So you'll notice right here when they plugged in a 0 for x, the result that they came out with was 3. They're doing two different functions here. So they had g of x and h of x. So if I'm just going to look at g of x for this one. But when x was 0, the result was 3, right? So they had this table of values that was given to them that they're trying to use to come up with the values for a and b. So if you plugged in a 0 for x and we come out with 3 as our result, that's simply because if I have something like this, if I'm plugging in a 0 for x, right, well, what always happens when we raise something to the 0 power, it doesn't matter what this number is, its value becomes 1. So that's like saying 1a is 3. And so just using that value of 0 tells us what the leading coefficient is. And then as far as getting our base, we can look at just the next number in line here. So if we said, well, what if x is a 1? So keep in mind we already now know that a is 3. If we plug in a 1 for x, the result was 6. And so all I would have to do is divide that 3 over, and that tells me my base was 2. And so once I know those two key numbers, I can say, okay, so the general function for g of x was 3 as my leading coefficient, 2 was my base, and we leave x as our variable. And so that's all we have to do. So just we look at the correct numbers, it makes figuring those out pretty easy. So on this next page, if you wanted to give one a shot here, I circled number 11. So if you want to give that a try, see if you can come up with the exponential function for that. So just the general layout for h of x would look something like this. So we're saying h of x equals ab to the x power. So if we look at this guy right here, so when we plug in a 0 for x, all right, so if it looks something like this, the result came out to be 4. So really simple, because that's just like saying 1 times a equals 4. So we know our a value is 4. And if we just look at maybe the next number in the list, you could really use other numbers for this, but to the first power is going to be the easiest because then you don't have to deal with roots. So if we just said, so 4 is now our a value, and b to the first power came out to be 0.8, then all we have to do is divide that 4 over, and that tells us what our b value would be. So if we divide 0.8 by 4, we're going to get 0.2. And so there's our two key numbers that we needed in order to set up our function. So we now would just say, so therefore h of x is equal to 4 times 0.2, which you could write that as a fraction if you'd rather, call that 1/5. Doesn't really matter. It'll come out looking like this. And you could always then check numbers. Like if you ever, for whatever reason, weren't sure, you could always test a number. So like if I plugged in -1 for x, is 0.2 to the negative first power times 4 equal to 20, right? And if it works out for those numbers, then we know we did it correctly. So let me take you down to these guys, getting back into our transformation rules. So there is a green box on page 249. Let me just show it to you really quick. So here's what our parent function looks like for exponential functions. I know you guys have seen this before, but anytime our base is a value greater than 1, then we're going to get this exponential growth curve that you see right here. Obviously, a key point on that graph is it will always pass through 0, 1. So it doesn't matter if your base is, or if you're looking at a decay graph or a growth graph, if you plug in a 0 for x, right, anything to the 0 power is 1. So all these graphs should pass through 0, 1. As far as the parent function goes. So whenever we start comparing to the parent function, that's one of the main values we always want to consider is what would happen to that point. And then the other one that we would probably consider next would be, well, if I plug in a 1 for x, then my y value is just going to be my base, right? Because let's just say this was a base of 3. Well, 3 to the first power is still 3. So whatever that base is becomes the y value if you plug in 1 for x. So we got growth that way, we got decay, or a decreasing graph if your base is a value between 0 and 1. Notice this does not take into account negative exponents, because remember what negative exponents do they would flip your base, and that would basically flip these rules. So we're not looking at it that way. We're just looking at positive exponents for these parent functions. So let me go back to some of these examples. So if we had 3 to the x as our parent function, so again, we already know it's going to pass through 0, 1, and since 3 to the first power is 3, we know it would also go through the point 1, 3. And so you can see our growth curve approaching infinity to the right, approaching 0 to the left, looking something like that. So what would happen if 3 to the x became 3 to the x minus 2, or to the negative x, or whatever, times 2? So as you're looking at these same transformation rules that we've already been using all year long, anything that is attached to x is going to affect your graph left and right. Typically does the opposite of what you would expect. So if I see x minus 2, obviously that is attached to x because it's part of the exponent, and we always do the opposite. So we would go to the right 2 units. So I would take those 2 points, bump them both to the right 2 units, and then I could redraw my curve, right? So same thing with the negative x. Again, it's attached to x, so I know it's going to reflect across the y-axis, right? Because it's going to reflect this graph to the left and to the right across the y-axis. And again, he wouldn't move, but this is where it helps to have a point like this. If you had a point like 1, 3, we know, according to these rules, it's going to become negative 1, 3, and so it would flip over to here, and here's where you would now be drawing your curve. If you put a 2 in front, so remember this is our stretch or shrink, so if the 2 is not attached to x, like this one is not, then we are looking at a vertical stretch. So we would simply multiply it times our y value. So if I were to take a point like 0, 1, that would become 0, 2. And a point like 1, 3 would become 1, 6. So if you just stick with the same rules that we've used all year so far, should be in good shape for these. So let me take you to these graphs. So these are what I was just describing that you have on this next page. You can see how the first one just shifted to the right 2. You can see how that second one just did the reflection across the y-axis. And then you can see how we have the vertical stretch for that third graph. Always look at the scale on these because they don't always count by ones, and so that can look a little confusing. So just be careful. Like if you look at these guys, these are counting by 2s. And so that's why, like we mentioned a second ago, I have a point at 0, 2 right there. So we're going to try some of these. I altered the base function here, and so instead of it being 5 to the x, I made it 2 to the x, because if your base is 5, your numbers get really big, and then it's hard to put on these graphs. So I shrunk the number to make it a little more doable with the numbers on the grids on the next page. Do these two right here. So you have g of x equals negative, that's going to be 2. It says negative 5 to the x, but like I said here, I'm changing your base to a 2. So for number 15, we're going to have a negative 2 to the x power. So I want to make sure we can apply that negative correctly. Notice this is not attached to the 2 because there are no parentheses surrounding it. So it might even be easier if you saw it like this. Right? Recognize that that negative is out front. It's our leading coefficient. It's not attached to the base. And as far as 16 goes, again, we're going to see this as 3 times 2 to the x. So I'm going to write it this way. But if you want to try these ahead of me, then go ahead and give these a shot on the next page. You can pause the video if you want. So how are we going to apply that negative? So on the one that we did here, the negative was attached to x. So it went left and right. But now it's out front. So now it's going to go up and down, which means we're going to reflect across the x-axis. So I already rewrote these guys here for you. So if you have these printed, here's what we were looking at. So I started with just having the parent function drawn in here, right? So if I applied the negative to that, Well, we know it's simply going to reflect across the x-axis. The other way to say that is simply, because it's out front, just like a vertical stretch or shrink, like what you would do with this one, I'm simply going to multiply that times my y values. So I would be taking a point like, let me give it an easy one. So if I had a point like 0, 1, right, it's just going to become 0, negative 1 as we move it down, which means I made this guy a little too small. So he should have been right there. So I have 0, negative 1. Again, a point like 1, 2 would become 1, negative 2. Right? And it's going to head downward and downward. So I'm not going to replot all those points, but here's just a sketch of it. So it'll be pretty close. So we should get that reflection across the x-axis up and down. As you look at this one, again, anytime you see that number out front, not attached to x, it just becomes a vertical stretch or shrink. So I would just be multiplying my y coordinates by 3. So if I were to take a point like, it's a little tougher with the decimal, so that's why I'm trying to use these whole numbers for you. But if you take a point like 0, 1, it would become 0, 3. So he's going to move up to here. This guy, I think that was my 1/2. So if I multiplied him by 3, he becomes 1.5. And then I'll just do one more point here. So a number like 2, 4 would become 2, 12. So you see how this comes off our grid real quick. So we should get something like this. It's still going to approach 0 to the left. It just becomes a taller, steeper graph when you apply that vertical stretch. All right. Let me do one more with you that they didn't have on there, but I wanted you guys to see this, where I give you like several different things that you have to do. So I laid out all the points from the parent function first. These are the same ones I had plotted up above for those parent functions. So, but now you have 3 things going on. Sorry, yeah, 3 things. You have a reflection, we have a stretch or shrink, we also have a horizontal shift. So I wanted to remind you guys, consider our Shy 15 acronym. Make sure we do things in the right order. Sometimes it matters, sometimes it doesn't, but if you want to be safe, I would always follow this pattern of doing things. So the first thing I want to start with is my stretch or shrink, which in this case is going to be that 1/2. Something to consider on this, because how do you always apply a stretch or shrink like this out front? Well, you just multiply it times your y value, right? So what if we cut this down to one less step, right? Because what I could say is, well, I'm going to multiply my y values by 1/2, and then a little later down, I can do my reflection across the x-axis down here, right? So you could do it in 2 steps like that because of the negative, or if you really wanted to do it in just 1 step, you could just say, well, let's just multiply my y coordinates by negative 1/2, and that will take care of the shrink as well as the reflection at the same time. Okay, and then we're also going to be subtracting 1 from our x's. So these guys that I'm looking at right here are just going to affect the y coordinates. So I'm multiplying all of my y coordinates by negative 1/2. So I'm looking at numbers like negative 1/8, negative 1/4, negative 1/2, negative 1, negative 2, negative 4. So that takes care of, it applies the negative, so it takes care of the reflection, and it applies the 1/2 to take care of the shrink. And then if we go left 1, just means we're going to subtract 1 from all of our x's. So at the same time, let's subtract 1 from these x's to create our new set of points. And so all we'd have to do now is just plot those values to create the new graph. And let me just plot a couple of them. So like negative 2, let's do negative 1, negative 1/2. It'll put me about here. 0, negative 1. 1, negative 2. And 2, negative 4. So we're just connecting the dots here, creating that new graph. So usually when you have multiple rules, definitely tougher to do it visually, like just a basic reflection is. It's better to really lay out the numbers and apply those rules to the actual points on the graph. Nearing the end here, stay with me, but we're going to be looking at our base of E. You guys learned about this before. Let me take you to our book really quick at page 251. Come on, book. All right, so a couple things I wanted to show you on here. One was, this is where E comes from. If you have this function, as x approaches infinity, or in other words, as x gets bigger and bigger and bigger, you get closer and closer and closer to this value that we use to we just use the letter E to represent that value. But you can see right here, if you were to actually graph this function, as you go farther to the right, you are getting closer and closer to that red line that you're seeing right there on the graph. And that red line has this value. So this value, about 2.71, is usually what we round it to. So here it is kind of laid out for you down here. So for this value, this is the number we use for E, right? This is the value that we are approaching as x gets bigger and bigger and bigger. So anyway, that's where it comes from. And then the other thing I wanted to show you on here was just the parent functions. Because E is a number greater than 1, it looks exactly like our exponential growth function when we use it as a base right here for B, right? So if our base is E, it's like any other exponential growth function where the base is bigger than 1. It's going to look something like this. If your exponent was negative, so here's where the negative exponent thing comes in. If your exponent's negative, remember what that does is it flips your base upside down. So if that k value is a negative, so let's just say your exponent was negative 2x, right? Well, if I'm going to flip this thing upside down, now it becomes 1 over 2.71. Now I'm looking at a base that is smaller than 1, and that's what's going to create that exponential decay function, just like we saw a little earlier on in this video. So keep those things in mind. Let's go through a couple of these graphs. So I already laid out the numbers for you for the parent function for y equals e to the x. So I'm just simply going to transform these numbers with stuff like this. So whenever you see that 2 right there, first things first, it is attached to x. Therefore, I have to apply it to my x's. And remember that the x stuff does the opposite of what you would think. So even though I see this as 2 times x, I'm going to divide my x's by 2 in order to take care of that 2 up there. So my new set of points, my y values won't change, but these guys would be cut in half. So now I'm going to get something more like this. So if I just plot these, and I'm just keeping the same y values here. So let's see, if I had -1 and then 0.14, super tiny. Hard to see the difference on that one. If I did -1/2 and 0.4, we're going up a little. These will be a little more clear here. So I'm still looking at 0, 1, still going through that point. Looking at 1/2 to 2.7. And then we are looking at 1, 7.4. So you can see what it does to that graph. So we would have called this a horizontal shrink, or you really could also see it as a vertical stretch. And we've talked about these earlier on in this year, but don't forget that a horizontal shrink is really the same thing as a vertical stretch. Just like a horizontal stretch is the same thing as a vertical shrink. It's really just a matter of how you want to apply it to the numbers within your table. But you'd come out with the same graph. So let's take those same numbers and do something like this. So if I put the 2 in front, he is not attached to x, therefore I would apply this to my y values. And the y values are just straightforward. I would multiply them by 2. So I would take those same parent function values and multiply the y coordinates by 2, so it becomes 0.28, 0.82, what was that, 5.4, and that would be 14.8, right? So it's just going to give me that vertical stretch. And typically you don't see it with the earlier numbers. It's kind of the bigger ones that you start noticing the real difference in the curve. So I'm going to start at 0, 2, we said was going to be one of our new points. Those little ones are so close together you almost don't see the difference on a graph. So 1, 5.4, be like around there. And then the last one, the 2, 14.8 is going to be like way off the graph. So it is skinnier than the previous one that was on there. So it would be something like this. But we'd still see a difference for sure. What if we did something like e to the negative x? We've already talked about some of these today. So if it's attached to x, we know it's going to go left and right. So if we did the reflection across the y-axis, simply taking these points and putting them over here. So we're going to get the curve reflecting over that y-axis. Going to look something more like this. And that is it for lesson 1.